Welcome back. Today we're going to talk about the LQR problem, which is a very special case of the optimal control problems which we discussed in the previous lecture. So we're just going to start off by defining what the LQR problem is, both in the discrete and continuous time cases. Then we're going to take a kind of more in-depth look at the solution to the discrete time case. This is where we'll spend the most of our time during the lecture. Along the way, we'll do a little bit of review of kind of some basic fundamental ideas from dynamic programming. And then finally, all the way at the end, we'll maybe very briefly talk about the continuous time case if we have time. So just as a quick side note for why we're doing it in this order, for LQR, the discrete time case I think is a little bit trickier to solve than the continuous time case. So we're going to kind of focus our efforts on there. So maybe one of those rare occasions where discrete time is a little bit harder. Okay, let's get started. So I want to begin by talking about the general setup for the LQR problem. So what is the LQR problem? Well, first I want to kind of motivate this problem by, kind of discussing these optimal control problems which we introduced last time, okay? So let's say last time, what did we do? Well, we introduced a class of what we said were basic linear optimal control problems. Okay? So what I said is the discrete time basic linear optimal control problem is the problem where we're taking an infimum or minimum, you could think of it as, over inputs going from 0 up until time n minus 1. This is going to be a subset of some input space u, which is maybe itself a subset of Rn. We're also going to be optimizing over a sequence of states going from 0 up until n. It's a subset of Rn. We're going to try to minimize the cost function, gn of xn, where gn is just some function of the state, plus this cost that gets accumulated from 0 up until time n minus 1, right? So we go from k equals 0 up until time n minus 1. So this is g of x of k, u of k, k. All right? So basically what we're doing at each step from 0 up until this integer time n minus 1 that we've specified, we kind of accumulate this cost g. Okay? So this penalizes stuff that happens along the way in our optimal control problem. All right? And of course, this is going to be subject to our dynamics, right? xk plus 1 equals axk plus buk, right? This should hold for all k in this interval 0 up until n minus 1. And finally, we should have some initial condition, right? X of 0 equals x naught. Okay, so this was this kind of structure of this basic discrete time linear optimal control problem, right? So some key aspects were we have what's called a finite horizon. So we have a finite horizon, which refers to the length n of the optimal control problem is less than infinity, right? So we're only interested in doing some optimization over a finite period of time. Now, what else do we have? Well, we also had the structure of accumulated cost, okay? Where we have this sum term that we kind of build up over the horizon, right? And this particular structure of accumulated costs was particularly amenable to solution techniques such as dynamic programming, right? Which we'll kind of review in a few moments once we start talking about this LQR problem. Okay, so my general claim last time was that, once we introduce this class of basic linear optimal control problems, we can use techniques such as dynamic programming to develop general solution techniques, right? To kind of figure out what's going to happen in general. But now what I want to do is, I want to kind of focus in on the structure of Gn and G, okay? So there's a couple things that I want to talk about, right? So what should Gn and G actually be, right? So what are some common goals that we have in control theory? What might we like our optimal control problem to emphasize? Well, one common goal is stabilization. So this is sometimes also referred to as regulation. Okay? And what we want to do is we want to keep our state close, which I'll just put in quotes, to the origin. okay? So we kind of want to make sure that our state doesn't stray too far away, all right? Now, in terms of this general linear optimal control problem that we introduced up here, nothing about g and gn says that, okay, this is particular, we're going to remain close to our origin at all times, right? The structure of our cost function doesn't really encourage this, okay? So let's try to brainstorm what sort of cost function might encourage this sort of regulated behavior, right, where our state stays close to the origin. So what cost encourages regulation? Okay, well, something really simple that we could think of, right, is maybe we could penalize the norm of x, right, or let's say the 2 norms squared, right, because that is a really easy form, okay? So let's try to penalize this at every time step, and, maybe we don't want to use huge inputs as well, okay? So let's say we're also going to penalize our input u at each time step, okay? So if we go ahead and do this, what might a nice form for our cost function be? Well, something that's kind of natural if we want to perform this regulation problem while at the same time keeping our input small. Maybe we want to minimize xn, 2 norms squared, plus the sum going from k equals 0 up until n minus 1 of x at time step k, 2 norms squared, plus u at time step k, 2 norms squared. Okay? So this is a candidate cost function. Candidate cost function. It seems like it might at least be a little bit relevant to this stabilization problem, right? Or at least to this regulation problem where within this interval 0 up until time n, I want to kind of stay close to the origin, right? Okay, well, kind of take a few moments and think about whether this cost function is sufficiently general, right? Does this always kind of give us what we want? Okay, so I'll assume you've taken a moment to give this some thought, right? Now, how do we generalize this? We generalize this. And is there actually a need for generalization? Well, what we might want to do is we might want to prioritize some states over others. Let's say my vector is in Rn, right? Maybe let's say I really care about what my component x1 is doing. I really want to make sure that x1 is close to the origin. Maybe it's fine if some of the others go a little further away, right? I want to put a lot of weight on this vector, or on this component x1, right? Now, maybe at the same time, let's say I don't care so much about my inputs versus my states. Well, I might want to put a lower cost on my inputs versus my states, okay? So I might want to trade off between inputs and states. Okay? So how am I going to do this? Well, maybe what I could do is I could, take some matrix C that just picks up some kind of valuable component of my state, and I can use that to kind of weight the different components of the states and to make sure that those desirable components don't grow too large, okay? So one approach is, instead of minimizing xk, 2 norms squared, let's minimize, let's say some matrix C times xk under 2 norms squared, okay? But what structure does the C times xk 2 norms squared actually have? If we go ahead and expand this out, then what we're actually trying to minimize is xk times xk transpose C times xk, right? If we just take cxk transpose cxk, then this is kind of what we get, all right? Now, for any matrix C out there, right, what this is going to be equal to is an xk transpose q times xk, all right? Where q equals C transpose C is going to be some positive semi-definite matrix, okay? So this kind of suggests that as a generalization, right, if we want to prioritize some states over some other states, this xk transpose qxk, which is a positive semi-definite quadratic form, might give us this nice generalization that we want, right? Now, similarly for the inputs, what I can look for is a uk transpose r times uk, all right? Now, as opposed to the state where, I have some positive semi-definite form, for the input, I'm going to want a strictly positive definite form, And the reason for this is that if R has a non-trivial null space, I can end up with inputs that blow up to infinity, right? Because some input components just might not be minimized at all if R is only PSD, okay? So what are we going to have? Well, we're going to have a cost structure of, let's say, x at time n transpose times some matrix Q final times x at time n plus the sum going from k equals 0 up until n minus 1, xk transpose times q times xk plus u at k transpose r at uk. All right, where here I'm going to take qf and q as symmetric positive definite matrices, positive semi-definite, and I'm going to take r as a strictly positive definite matrix, okay? So just as a quick side note, I've introduced this extra matrix QF just so we can kind of tune this terminal cost a little bit differently, right? If we really want to emphasize that we need to be at some certain final state, or we want this final state to be really small, I can weight QF higher than Q, or higher than R, for instance, to kind of balance these things out. Okay. So this general structure of cost will lead us to the discrete time linear quadratic regulator problem, okay? So you can kind of guess this name linear quadratic comes from the fact that we now have all of these quadratic forms in our cost function and our dynamics are linear, okay? Okay, so this leads us to the following definition. So definition, which is the discrete time LQR problem, okay? So what I'll say is consider a discrete time dynamical system with a state equation x at time k plus 1 equals axk plus buk. All right, so the finite horizon discrete time LQR problem is going to be the problem infimum over u going from 0 up until time n minus 1. And here we're just going to take the u's to be a subset of Rm, okay? So these inputs aren't actually restricted. We're going to go over x going from 0 up until time n, which is a subset of Rn. And we're going to penalize exactly this cost up here, okay? So we're going to have xn transpose qf times xn plus sum going from k equals 0 up until n minus 1 of xk transpose q xk plus uk transpose ruk. And this is going to be subject to, of course, our dynamics, xk plus 1 equals axk plus buk. And, this constraint is applied over our whole horizon, right? k going from 0 to n. And this is going to be subject to some initial condition, x of 0 equals x naught, okay? So here, we'll always assume that qf and q are going to be symmetric n by n matrices, which are positive semi-definite. And then R will be a symmetric m by m matrix, right? Where R will be strictly positive definite. Okay, so this is the discrete time LQR problem. What would we say about the continuous time case? Well, what we're doing over here is we're accumulating a quadratic form over a horizon, right? So how do we accumulate cost in the continuous time case? Well, we use an integral, right? Instead of this sum, we could just replace this thing with an integral, and then we should get a continuous time analog of this problem, right? Okay, so this leads me to the definition of the continuous time finite horizon. So I should specify this discrete time problem up here that I've specified is also finite horizon, right? Because n is going to be some integer that's less than infinity. So continuous time finite horizon LQR problem. Okay, so what I'll say now is consider a continuous time dynamical system with state equation x dot of t equals ax of t plus b times u of t. Now the finite horizon, finite horizon continuous time LQR problem is the following. So now it's going to be in FEMA, instead of over a sequence, it's going to be over an input signal, right? Where U is going to be some piecewise continuous signal from R into Rm, right? X, which is going to be the trajectory of the system, will at least need to be continuous, right? From R into Rn. And what we're going to minimize is effectively the analog of this cost function, but in continuous time, okay? So now for some final real number t, I'm going to minimize x of t transpose times a qf, x at t. And instead of the sum, I'm going to have an integral term that accumulates cost, okay? Because this integral accumulation will be really just the continuous time analog of this sum accumulation, okay? So I'm going to take the integral from 0 up until time t of x of tau transpose qx of tau plus u of tau transpose ru of tau d tau, okay? And this is going to be subject to my dynamics conditions, which is x dot of t equals ax of t plus b times u of t, okay? So this holds for all t where u is continuous, right? This is just a minor technical detail, which we talked about much earlier in the course, right? Where this derivative condition can't hold where u has jump discontinuities, right? But this is a minor background condition. It's not something we're going to focus on too much today, okay? So this is the first condition, and then second, we're going to say x of 0 equals some x naught, okay? So here, what we have is that qf and q are again symmetric n by n matrices, which are both positive semi-definite. And then I have R will be a symmetric m by m matrix where R will be strictly positive definite, okay? So this is pretty much the same problem that we've had above, right? Just directly translated into continuous time, okay? So this is this continuous time finite horizon LQR problem. Okay, fantastic. So what we've done is we've just laid out two sort of interesting problems which seem to be related to the regulation of a state, right, over this finite horizon 0 up until n, or 0 up until time t in the continuous time case, okay? So what we're interested in doing is we're interested in keeping the state close to the origin, or at least some component of the state close to the origin, while at the same time not using super large inputs, all right? So that's all that this kind of fancy optimization problem is doing. Okay, so how do we actually solve this problem? Well, what are we going to do? You know, in the previous section, right, we had kind of discussed, all right, when we have cost functions that have this accumulated form, we can use dynamic programming, or kind of in the continuous time case, we could use something called the HJB equation, right, to kind of solve these optimal control problems. How are we actually going to put these things into practice? Well, this is what we're going to consider next, okay? So what I want to do now is I want to really go through a kind of detailed derivation of the discrete time LQR problem, okay? So what we're going to do is we're kind of going to go through the steps of dynamic programming for the discrete time LQR problem. Along the way, I'll just provide a basic review of the DP material we covered in the previous lecture, in case you haven't had the chance to watch that, okay? All right, let's get into it. So I want to start off with a quick review of dynamic programming. Okay, so what did we say last time? Well, we had introduced this class of basic optimal control problems, right, where we want to solve this minimization of u going from 0 up until time n minus 1, x going from 0 up until time n of gn xn, plus sum going from k equals 0 up until n minus 1, g of xk, uk, and k, subject to the constraints xk plus 1 equals axk plus buk, and x at time 0 equals x naught, okay? So where does dynamic programming kind of fit into the solution of this optimal control problem? Well, it's kind of motivated by the following idea. If we're to kind of take one of these abstract problems and try to solve it straight up, that's something that's really hard to do, right? So this is a dynamic optimization problem. Dynamic optimization problem, which is to say, we kind of have this state equation embedded in there, right? This is something that makes this problem really tricky to solve, right? We're going across n steps. We're optimizing over this entire sequence of inputs. We have this really complicated cost function. And we actually have our system dynamics kind of embedded as a constraint on this problem, okay? So these things are really hard to solve in general. Now, the insight of DP, or dynamic programming, we can kind of split up our problem into easier to solve pieces, right? And once we perform these splits, and maybe we can kind of solve these easier pieces of this optimal control problem, we can kind of piece together these little solutions to figure out a solution to our big overall problem, okay? So let me go through how we actually perform this split, right? Let me start off with a little bit of motivation, okay? So what's a really basic way to split up this problem into some sort of easier problem? Well, what we can do is we can kind of try splitting up the cost function. The cost function. Okay, so what I'm going to do is pick an integer, m, which belongs to my horizon. Let's say I'll pick it between 0 and n minus 1, so I have one step left over, okay? Now what I'm going to do is I'm going to rewrite my cost, which is kind of split down the middle, okay? I'm just going to go ahead and split it into the cost that we incur before time n and the cost that we incur after time n, okay? So if I do this, what I'll find is I'll get the sum, k going from 0 up until m minus 1 of g of xk, uk, and k, right? So my first term, this represents the cost before m, plus this remaining cost to go term after n, okay? So I have g of xn plus the sum will now go from k equals m all the way up until n minus 1 of g of xk, uk, and k, all right? So this is my cost, I'll say, to go after and at, oh my gosh, there we go, and at time step m, okay? So what we've done is we've just picked some integer m, right, which is kind of in the middle of our optimal control problem horizon. We've just said, okay, let's go ahead and let's split up our cost function into the cost before time step m and the cost after time step m. And let's see what we find, right? Well, kind of take a moment and take a look at this new split up cost and see if you kind of recognize anything, okay? All right, so I'll assume you've given this a look. What you might notice is that this cost over here has a very, very similar structure to this cost, right? All that we're doing is we're now starting our sum at m instead of at 0, okay? Other than that, we have the same sort of cost structure, all right? So the idea is let's try to solve the simpler to-go problem, which I'll call inf over u going from 0, inf over u going from m up until time n minus 1, x going from m up until time n of gn of xn plus the sum going from k equals m up until n minus 1, g of xk, uk, and k, all right? It's going to be subject to our same dynamics. X at k plus 1 equals ax of k plus b times u of k. And subject to x at time m will be equal to xm from your full problem. Okay? So this is an easier to solve problem, right? And the thing is, it really has the same sort of structure as our original problem, okay? Only now it's much smaller because we're starting from step m instead of step n minus 1, okay? So the basic idea is kind of instead of going ahead and solving this huge optimal control problem all the way at once, we can solve this simpler to-go problem, right, which kind of starts at step M, and maybe using these solutions to these simpler to-go problems, which maybe we'll be able to find, we can kind of piece together solutions to our original problem, okay? All right, so how are we actually going to get this done? Well, here's what we're going to do. What's a problem that you kind of notice with this solution to this to-go problem? Is this something we can easily solve? Well, no, probably still not, right? We still have a reasonably large optimization if m is going to be some arbitrary number in this horizon. And if eventually we want to figure out what our solution to our large optimal control problem is, then we'll need the optimal solution to this to-go problem going from times 0. Right, which is just the same thing as our original optimal control problem. So we haven't really, as of yet, kind of fixed our issues, right? What we want to do is we want to kind of figure out a way, which is a little bit clever, to use these to-go problems and kind of get nice, simple optimization problems, okay? So here's what I'm going to do. There's one sort of other problem that really sticks out with this to-go problem, which is if we're trying to solve this optimization problem over our entire horizon, and we try to solve this to-go problem, we don't actually know where we're going to be at time step m, right? Like, how do I actually pick this m over here? So one insight is, right, instead of solving this optimal to-go problem for, just one given state x of m, we could try to solve it over the entire state space, okay? So what I'm going to do is, I'm going to say, let's try to solve this for an arbitrary state x, okay? So this is now an arbitrary state. Because, if I'm trying to solve this to-go problem and still have it be relevant to, my original big optimal control problem, I don't actually know where I'm going to end up at state m, right? If I just fix an arbitrary state, then I should be able to figure it out, right? Because that covers my entire state space. So what I'm going to do is I'm going to define a function called j star of x comma m, which is the optimal value of this entire optimal control problem, okay? So this is called my optimal cost to go function, okay? So what it does is it takes in this arbitrary state where my system is starting, and it takes this time step m where I'd like my optimal control problem to start. And this is just equal to the minimum value of this optimal cost to go optimization problem starting at step m, okay? Now, the really important part about this is we don't have a fixed state in this, okay? Since this is a function of x, this function is defined across my entire state space, okay? So what I want to do now is I want to figure out a nice method to solve for j star of x comma m, okay? So remember, these are still reasonably hard optimization problems to solve, so I want to figure out if there's a really nice, easy way to figure out what these j stars are, okay? So one insight that's really important into kind of figuring out these j stars is something called the principle of optimality, okay? And what this effectively says is that if a control law is optimal for a full control problem, full optimal control problem, it also needs to be optimal for every to-go problem. Okay? And effectively, the reason for this is, let's say we had some control law that was optimal for our full optimization problem, right? This one up here, but wasn't optimal for one of these to-go problems. Then let's say, this to-go problem M, we have some kind of better control law. Then what we could do is we could just take our supposedly optimal control problem our supposedly optimal control law for our full problem. Once we get to step M, we just switch to this apparently better control law, which is actually optimal for this to-go problem, okay? Then using that, we would end up improving our costs, and that would contradict that, our original optimal control law was in fact optimal, okay? So what this principle of optimality states is that if we have an optimal control law for our full problem, then it kind of needs to be optimal for every single sub-problem as well. All right? So this really important principle actually enforces a relationship between these different j star of x comma m's. All right? So what this implies is that j star of x comma m is equal to the infimum over u belonging to our input space of the cost at time m. Okay? So g of x, u, and m, plus your optimal cost to go at your next state. Okay? So my next state is going to be just ax plus bu, right? And at time m plus 1, okay? So what the principle of optimality states is that I need to be optimal at step m, and then I need to be optimal after step m, okay? So we have this important idea, right, which is that if we're optimal at step m, then we need to be optimal in every to-go subproblem after step m, all right? Otherwise, we would contradict this principle of optimality. Okay, so what this does is this enforces this nice recursive structure amongst all of these optimal cost to-goes, right? So let's go ahead and just state a theorem that says, all this dynamic programming stuff actually works, right? So theorem, which is dynamic programming. And what this says is that consider a sequence of functions which are defined according to the following recurrence. So we're going to have a j at time step n of x is just going to equal our terminal cost term over here. Okay, so we're going to start all the way at the end. So we have gn is equal to gn of x, right, where this is the same function that we highlighted up there. Now I'm going to have, for each value less than n, I'll have jm of x is equal to this infimum over u and u of g of x, um, plus j star of ax plus bu at m plus 1, right? And this is going to hold for m equals 0 all the way up until n minus 1, okay? Then what I have is that each jm of x will actually equal to the optimal cost to go starting at state x from time m, okay? This holds for all m in 0, n. All right, so effectively what this confirms is that, if we execute this recurrent relationship between each of these functions jm, what we get is exactly the optimal cost to go, all right? Now further, if there exists a control law, u equals, let's say, k star of x comma m, where x is any state in Rn, and m belongs to this interval 0 up until n minus 1, such that u equals k star of x comma m achieves each infimum, right, where each of these infimums will just be these up here, okay? Then k star must be an optimal control law. Control law for the full problem. Okay? So effectively what this says is that if we execute this recurrence, right, where in each step of this recurrence we're solving for an optimal control law u as a function of x, then what we can find is an optimal control law for our full problem, okay? So what this method of dynamic programming does is it takes our original really complicated optimal control problem and it kind of just breaks it up into a sequence of simple single variable optimization problems which are kind of nice and easy to solve, right? Now once we have this and we solve each step of this recurrence, we can go ahead and kind of reconstruct what our full optimal control law should be. Okay, very cool. So that's kind of the end of this basic dynamic programming review. Now what I want to do is I want to apply dynamic programming to solve the LQR problem. Okay. So let's apply DP to solve the discrete time LQR problem in which we're solving the minimization of 0 up until n minus 1, x going from 0 up until time n of xn transpose qf xn plus the sum going from k equals 0 up until n minus 1 of x of k transpose qxk plus u of k transpose ru of k, subject to xk plus 1 equals axk plus buk, right? And that holds over my whole horizon. And then x of 0 equals x naught, okay? So my goal is to find an optimal control law, which I'll call KLQR, and that takes in a state in Rn, and it takes in any integer in 0n minus 1, right? It returns a value in Rm. And I want this to solve the LQR problem for any state in my state space in Rn, okay? So my goal is to kind of figure out globally what the solution to this LQR problem is, all right? If I give you any x naught, or I give you any x1, x2, xn minus 1, I should be able to figure out what the optimal control law according to this LQR problem is at that state, okay? All right, so what are we going to do? Well, what is our dynamic programming algorithm state? If we can find a sequence of functions j naught, jn, satisfying the dynamic programming recurrence, right, which we just outlined in the theorem above, which follows from the principle of optimality, and a sequence of inputs as a function of x, achieving the infimum, then we can solve the LQR problem. Okay, so let's go ahead and put dynamic programming to use to actually construct a solution to this LQR problem. Okay, so what does the dynamic programming theorem state? Well, it states if we could solve this recurrence, right, we can kind of work our way back towards a solution. All right, so the first step of this is to identify j at step n. All right, once we have that, we can start applying this recurrence to step our way backwards. Oops, just noticed actually I should make this like that, and this should be an m plus 1. There we go, and keep my notation consistent. Okay, there we go, now we're good. All right, so what we want to do first is we want to identify what jn of x is, okay? Identify jn of x, all right? Now our optimal cost to go, starting from time n, is just going to be the terminal cost, right? So right away we see that jn of x is nothing more than x transpose qf times x, all right? So this is just our terminal cost. All right, great, fantastic. So now what I want to do is I want to go back one step, right? My dynamic programming theorem states that once I have jn, I should be able to solve this minimization problem to find jm, right? So what I want to do is I want to find jn minus 1 of x as my second step, right? And I'm going to find this as an arbitrary function of x because I need to solve it across my entire state space, right? So my jn minus 1 of x, according to this dynamic programming algorithm, should be the infimum over u and rm of my cost at time m, which I'm accumulating, right? So that's going to be equal to this guy over here, right? So this is going to be an x transpose qx plus u transpose ru, and according to dp, this is going to be plus a jn of my next state, right? ax plus bu. Okay, so let's go ahead and plug in our formula for jn and see if we could actually solve this minimization. Well, this is equal to inf over u of x transpose qx plus u transpose ru plus jn, which is just x transpose qf times x. So we'll have an ax plus bu transpose qf times ax plus bu, all right? So let me go ahead and expand this thing out. inf over u x transpose qx plus u transpose ru plus we'll have an x transpose a transpose qf ax plus then a, let's see, 2x transpose a transpose qf times b times u, finally plus a u transpose b transpose qf b times u. Okay, so let's take a moment and see if we could actually solve this optimization problem, right? Does this look like something we can solve? See if you could think of a method that we could use to actually construct a solution. Okay, so I'll assume that you've maybe thought of a method, and hopefully what you arrived at is that since each of q and qf is positive semi-definite and r is positive definite, we can solve this minimization by taking a gradient with respect to u, equate to 0, to solve for u, and substitute this u back in. Okay? So basically what we're going to do is that since q and qf are positive semi-definite and r is positive definite, we know that the solution to this optimal control problem, to this optimization problem, can be solved via differentiation, right? Because this is going to be a convex optimization, okay? So what we could do is we could actually find the value u, which exactly minimizes this by, equating with 0 and solving. And once we have that value of u, we can plug it back in, and that'll tell us the value of this infimum, okay? Let's go ahead and do that. So first what I'm going to do is, when I take this gradient, all the terms that don't have u are just going to drop out to 0, right? So what I want to do is I want to evaluate the gradient with respect to u of all the remaining terms that have u involved, okay? So I'll just directly jump to that. So the gradient with respect to u of u transpose ru, right? I'm deleting x transpose qx because u doesn't show up. I can delete the second term because u doesn't show up, plus we'll have a 2x transpose a transpose qf b times u, finally plus this last term, which is u transpose b transpose qf times b times u. What's the value of this gradient? Well, let's just go ahead and compute. What are we going to find? This is going to equal to 2 times ru in this first term, plus we'll have, we'll have a 2b transpose qf, since qf is symmetric. We'll have an a, and then we'll have an x. And finally, we'll have a plus 2b transpose qf b times u, okay? So what I'm going to do now is I'm going to say, okay, let's equate this with 0, and let's solve for my input u. So first what I'll do is I'll drop all of these 2's, right? And I'll kind of collect all the terms that have u on them. So if I do that, I'll find that I get an r plus b transpose qf times b multiplied by u will equal to a minus b transpose qf times a times x, right? If I just bring this other term over to the other side and just kind of delete all these 2's, right? And just cancel them out. Okay, now is this matrix over here invertible, right? If I want to solve for u, it kind of looks like I need to invert that matrix. Well, because r is positive definite, qf is positive semi-definite, it turns out that this sum is in fact positive definite, right? So if this sum is positive definite, it's invertible. So we can go ahead and solve for solve for u. So if I solve for u, then what I end up getting is a minus r plus b transpose qf times b transpose qf times a, all multiplied by x, okay? So what this gives me is it gives me my optimal control at time n minus 1 as a function of x, all right? Now what I observe is this optimal control law is actually a state feedback control law, right? I have some matrix multiplied by my state x, okay? This is kind of interesting. So what I'll do now is I'll go ahead and I'll plug back in to solve for my value jn minus 1 of x, okay? So I now have my optimal value, or excuse me, my optimal control, which solved this minimization. I want to go ahead and I want to plug it back in to figure out what Jn minus 1 actually is. Okay? So what I should have is I should have Jn minus 1 of x will equal to this infimum just with u plugged in, right? So if I go ahead and solve this, what do I see? Well, I'll get an x transpose qx plus, just for convenience, I'm going to call this big matrix in front of x. I'll just call it K, all right? So what do I get? Well, I'll get a K times x transpose R times K times x, plus in this remaining term, I'll have AX plus BKX transpose QF times AX plus BK times X, all right? Now, if I simplify this, what do I see? Well, I get an X transpose QX plus X transpose K transpose R, K times X, plus an X transpose times A plus BK transpose QF, A plus BK times X. So what I notice is that each of these will be a kind of quadratic form in X, right? So I can pull a bunch of X transposes out to the front. And I get a Q plus K transpose RK plus an A plus BK transpose QF times A plus BK, all multiplied by X, all right? So interestingly, if I just kind of call all of this some big matrix P at time n minus 1, I'll find that my optimal cost to go at time n minus 1 is actually a quadratic form, right? So I have an X transpose Pn minus 1 times X. Okay, so this is all very interesting, right? What I've done is I've shown that my optimal control at time n minus 1 is actually a state feedback control law, okay? So we have that our optimal control law at n minus 1 is a state feedback, or linear state feedback control law, okay? And then my optimal cost to go at time n minus 1 is a quadratic form. Okay? So how can we use this information to kind of solve my full optimal control problem, right? How can I use this to kind of continue solving this recurrence out? Well, the thing is, right, if I have n steps that I want to solve this recursion for, right, which is what's required for dynamic programming, I really kind of need to look for some pattern in order to figure out what's going to happen over those n steps, right? It doesn't really mean anything to solve a problem for n steps, right? I can't do a recurrence for n steps and then say, okay, I'm done, right? Because n is not a fixed number, right? N is arbitrary. So in order to solve this optimal control problem using dynamic programming, what I would need is to kind of really notice some pattern that occurs in the optimal cost to go at each step, okay? Some pattern that also kind of occurs in my optimal control law. So what does this first step suggest? Well, we found that our optimal control law is this linear state feedback control law, right? And further, what we found is that my optimal cost to go appears to be a quadratic form, okay? So what we conjecture is that the same sort of pattern appears, right? Our guess is that at each step, our optimal control law will be linear state feedback, and at each step, my optimal cost to go will be a quadratic form, okay? So what I'm going to state now is a theorem that kind of says this actually is true. And further, we're going to figure out an actual recurrence between these P matrices at every single step, okay? Turns out this is what gives us the solution to the LQR problem in this finite horizon case, okay? So let's state this as a theorem, which is the solution of the discrete time finite horizon LQR problem. Okay, so what we'll do is we'll say, consider the discrete time finite horizon LQR problem, say defined by matrices Q, QF, and R, which satisfy the usual regularity conditions, and a horizon N, okay? So the first part of this theorem is a statement about the optimal cost to go. All right. So this basically confirms this conjecture, which we just made above, which says that the optimal cost to go is a quadratic form in each step. Okay. So step 1 is optimal cost to go. All right. What we're going to say is for each k equals 0, going up until time n, the optimal cost to go function is a quadratic form j star of x comma k equals x transpose pk times x. And in particular, we're going to have that each pk will be a symmetric n by n matrix, right? It's going to be positive semi-definite as well, and it's going to satisfy this recurrence Pn equals Qf, and P at time step k will equal to this very long equation, A transpose Pk plus 1 minus Pk plus 1 times B transpose Pk plus 1 times B plus R, all inverse times B transpose Pk plus 1, my gosh, all times A plus Q, all right? Where this K holds for all between 0 and n minus 1, okay? So this equation over here is quite famous in control. So this equation is called the discrete time Riccati equation. Okay? So it turns out that this equation is not unique to the problem of LQR. Okay? It actually shows up in a lot of different places in control. Now, notably, you'll find that this appears in Kalman filtering as well, okay, albeit in a slightly different form. Okay? So equations of this form, where you have these kind of really complicated-looking quadratic functions of p, really show up a lot. These are called discrete time Riccati equations. Okay? All right. Now, secondly, we're going to have a statement about the actual optimal control law. So, optimal control law. All right. So, the optimal control law is the time-varying linear state feedback control law, which is going to be u optimal at time k will equal to minus, let's see, b transpose p at time k plus 1 times b plus r, all inverse times b transpose p at time k plus 1 a times x, all right? Where k will equal to 0 all the way until time n minus 1. Okay? So this is what the optimal control law as a function of x will always look like. Okay, fantastic. All right, so how are we actually going to prove this result? Well, you know, whenever we have proofs that involve these sorts of recursions, it kind of makes sense that we use some sort of induction argument. Okay? So that's exactly what we're going to do here. Now I'm just going to give you a sketch of this proof. Since, you know, due to this really complicated form of this discrete time Riccati equation, the full proof really just involves a lot of kind of grindy algebra, okay, that I think is maybe not super revealing. So I'll just kind of give you a sketch of how you kind of solve these things out, okay? All right. So how are we going to prove this result? Well, what we could do is we can use the dynamic programming algorithm, okay? So if we want to show that our optimal cost to go at each time step k is going to be x transpose pk times x, where the pk have this form, then we could kind of solve this dynamic programming recurrence, right? So we could solve the dp recurrence, or rather show that the dp recurrence, which starts with jn of x equals x transpose qfx, as we established before, and then m of x, or I'll say it as jk of x here, equals the infimum over u of x transpose qx plus u transpose ru plus this j at time k plus 1 of ax plus bu. We can show that this satisfies jk of x equals x transpose pkx for each k. Okay? Where these pk matrices are these matrices that are specified by this Riccati equation, kind of recurrence that we defined up here. Okay? So how are we actually going to show that this holds? Well, something that's interesting here is that instead of doing a forwards induction argument like we usually need to do, we need to use a backward induction argument. Okay? So here, our base case will be time step n, right? And since our recurrence is going backwards instead of forwards, right? Since we go from k plus 1 up until, or down to k, rather than from k until k plus 1, our inductive step will be assume it's true for time k plus 1, and then show it's true at time k. All right? So it works a little bit differently to a standard induction proof, and this is because our recurrence in dynamic programming goes backwards rather than forwards, right? We start all the way at the end of our control horizon, and then we iteratively solve these problems backwards in time, right? Like remember above, we started with jn, then we worked our way back to jn minus 1, and that kind of keeps going down until you get down to j0, okay? All right, so let me give you a quick sketch of how this induction argument works, and then we'll move on to talking about the infinite horizon case, okay? Well, let's start with the base case. So what do we have in the base case? Well, I want to show that Jn of x equals to x transpose times Pn of x, okay? So I want to show Jn of x equals x transpose Pn x, okay? So I know that I have Jn of x equals x transpose Qf times x. And if I look at the recurrence, which I kind of outlined up here, well, I just define Pn as Qf, okay? And Pn equals Qf, which means that we're good to go, okay? So the base case follows pretty easily. Now, what about the inductive case? Inductive case. So what I do is I assume for induction that jk plus 1 of x equals x transpose pk plus 1 times x, okay? What I want to show is that jk of x equals x transpose pk times x, where pk satisfies the discrete time Riccati equation, okay? So how am I going to do this? Well, all that I'm going to do is just kind of solve out this dynamic programming recurrence, right? So what I'm going to have is that jk of x will equal to the infimum over u belonging to Rm of x transpose qx plus u transpose times ru plus my cost at the next time step, right? jk plus 1 of my state at the next time step, which is ax plus bu, okay? Now, what I assumed for the sake of induction was that my state at the next time step was x transpose pk plus 1 times x, right? So if I just imply my inductive hypothesis, well, I get inf x transpose qx plus u transpose ru plus ax plus bu transpose times p at time step k plus 1 times ax plus bu, okay? Now, my next step is to go ahead and solve for u star achieving this infimum, okay? Because once again, since I'm assuming for induction that pk plus 1 was positive semi-definite, it turns out that this optimization problem is actually nice and easy for us to solve, right? It's a convex problem, which means I could just differentiate in u and kind of work my way out to a solution from there, okay? Now, what you'll notice is that this optimization problem for jk actually has the exact same form as the problem which we solved up over here, okay? Now, just in the place of qf, we have pk plus 1, okay? So what this means is that my optimal input will be precisely this, just with pk plus 1 instead of qf, okay? So I'm not going to repeat the details of that because it's the exact same derivation, okay? So the same derivation as above will suggest that my input, u star, will be precisely equal to minus b transpose pk plus 1 times b plus r, all inverse, times b transpose, get a little extra dot there, b transpose pk plus 1 times a times x, okay? Or, I could also call this k at time step k times x, all right, just for convenience. All right, so what this actually does is this confirms along the way that my optimal control law is of this form that I wanted, right? We get this kind of nice time-varying state feedback control law. Okay, so that actually confirms that along the way, which is nice. Now our next step is we plug u star equals kk times x back in to the jk minimization, okay? And what I would find is that jk of x will be equal to x transpose qx plus this u transpose ru, which is equal to x transpose kk transpose ru kk times x plus this x transpose a plus b kk transpose p k plus 1 times a plus b k sub k times x, all right? And, what I could do is I can then go ahead, pull out this x transpose q, then plus k sub k transpose r kk plus a plus b kk transpose pk plus 1 a plus b kk times x, all right? And then after lots of algebraic simplification, what I would find is that this ends up being precisely equal to x transpose times p at k times x, all right? So I find that this whole expression inside here actually simplifies to this Riccati equation term up over here, okay? So I end up getting precisely this form from inside my function over here, okay? All right. So again, this is the part of the LQR problem that just involves a lot of algebra that I think is not really super revealing, okay? So I'm just going to skip through it for the sake of time over here, all right? If you're interested, I'll include a full proof in the notes. We can go ahead and kind of map out all the details of this argument, okay? All right, so this is the basic induction argument, right? What you do is you go ahead, you say, all right, first I'm going to show that this holds for the base case, then for the inductive case, I assume that it's true for time k plus 1. Now for my backwards induction argument, right, I want to go back one step and show that it holds at time k, all right? So what we did is we solved for the optimal input at time k, we plugged it back in, and after this algebraic simplification, we find that it also holds at time step k, all right? So that kind of concludes our basic derivation. Actually, we're not quite finished yet, so I won't write the square. So this is the basic derivation of where this discrete time Riccati equation comes from and where this optimal control law comes from, okay? So I just want to go ahead and discuss one more quick point, okay? So one last point. So we claimed that the pk was symmetric and PSD, okay? So I quickly want to talk about how we would prove both of these, okay? So the proof of symmetric is just straightforward from the Riccati equation, okay? So if we just go ahead and take a look at our Riccati equation up here, then you just take the transpose of this and then you find that the transpose is in fact equal to the original thing, okay? Since this holds for all pk, or excuse me, for all k, then you can conclude that this is in fact going to be kind of symmetric at every step, okay? So that's fairly straightforward. Now, how do we prove that it is PSD, okay? Well, the nice thing is, PSD, we know that jk of x is equal to x transpose pk times x for all x in Rn. All right? Now, what else do we know about this function jk? We know jk of x is going to be greater than or equal to 0 for all x, since it is a minimum or minimization of a cost which is always greater than or equal to 0. Okay? So if we take a look at kind of this formula over here, what we're doing is we're taking a minimization of functions which are all going to be greater than or equal to 0. Okay? And since we're doing that, we conclude that jk itself needs to be greater than or equal to 0. But if we have that jk of x equals x transpose pk times x is greater than or equal to 0 for all x in Rn, and that pk is symmetric, this is in fact equivalent to pk being positive semi-definite. Okay? So what we do is we conclude that pk is PSD. All right? So this is the basic argument. For symmetric, we just verify this from the Riccati equation. For PSD, this is a fact that just follows from this pk coming from a minimization of a non-negative function. All right? So that kind of concludes our proof sketch of this discrete time LQR theorem. Okay, fantastic. So let me just go ahead and summarize what we've said real quick. What we've said is that if we want to solve the discrete time finite horizon LQR problem, what we do is we solve this recurrence, right? Just call it a discrete time Riccati equation over our horizon. And we generate a set of positive semi-definite matrices pk using this recurrence, okay? Now, once we have all these pk's, we can compute our optimal control law for all time, which just turns out to be this linear time-varying state feedback control law written in terms of pk, okay? So, this is maybe a slightly amazing fact, right? It turns out that our optimal control law is actually linear, right? We didn't specify anything about linearity for our problem, but linearity just happens to fall out as this kind of best control law for this problem, okay? So this is a really nice property that, maybe you shouldn't take for granted, okay? This isn't something that we asked to happen at all. It turns out linear feedback just happens to be optimal for linear systems, provided we're taking this nice quadratic cost. Okay, so next what I want to do is I want to talk about the infinite horizon case of the LQR problem. All right, so let's talk about the infinite horizon LQR problem. So all that we've done so far is we've talked about how we solve optimal control laws over some finite horizon, right? Where the value n that specifies my horizon is going to be some fixed finite integer, okay? Now, why do we want to consider the infinite horizon case, right? Why might we not want n to be finite? Well, one of the main things that we're interested in control is getting asymptotic behavior out of our system, right? For instance, stability of our system is an entirely asymptotic property, right? Stability is not something that we can determine in finite time, right? Rather, in order to determine if our system is stable in the sense of Lyapunov or asymptotically stable or exponentially stable, what we need to do is we need to verify that properties are holding in the limits as k goes to infinity, right? So we want to make any claims about asymptotic behavior of our system, we actually need to consider an infinite horizon control problem, okay? So what I'm going to do is I'm going to start out by writing out what the infinite horizon LQR problem is, all right? So we'll do our same infimum over inputs, but now instead of just taking inputs going from 0 until time n minus 1, I'm going to have an infinite sequence of inputs, right? Which I'll denote as u with this little bracket. It's going to be a subset of Rm. Likewise, we'll have an infinite sequence of states, x, which is a subset of Rn. Now, since we're taking n to infinity, there's no point of having a terminal cost, right? Because we don't really have a final state for our system because we're taking this limit, okay? So I'm just going to drop the terminal cost. What this leaves us with is the sum going from k equals 0 up until infinity of, let me draw that a little nicer. There we go. Of xk transpose times q times xk plus u at time k transpose r at time uk. It's going to be subject to our favorite conditions. X at time k plus 1 is equal to ax at time k plus bu at time k. This needs to hold for all k, now going from 0 up until infinity, and subject to some initial condition, x at time 0 equals x naught. Okay? So this is our infinite horizon LQR problem, right? We drop our terminal cost because there's no longer any notion of terminal state, right? And then we take our horizon n and send it off to infinity. Okay? So what are our goals in this case? Our goals. Well, we want to get an optimal control law with some asymptotic behavior. Okay? So now instead of considering n, since we're interested in asymptotic behavior of the system and getting optimal behavior asymptotically, we take n to infinity, right? Okay. So there's a couple of things to keep in mind about this problem, right? Now that we have this infinite horizon, we're not necessarily sure that this problem is even solvable, right? So we only say that the problem is feasible if there exists sequences u and x satisfying the constraints that give us finite cost. Okay? So we now see that, since we have this infinite sum, finite cost is not necessarily something that's a given, right? Let's say, our system is unstable and we have no control over that unstable part of our system. And, let's say Q is the identity matrix, and it certainly seems like this cost is going to blow up to infinity, right? So in order to actually have this problem be feasible, we're going to need to enforce extra conditions on the problem, okay? So what we need is, for feasibility, we need extra conditions on our system and on the problem, okay? So if we want to obtain finite cost, what's one thing that we need? Well, we need that this term xk transpose q times xk will go to 0 as k goes to infinity for an input signal. Okay. So what seems like a reasonable condition that'll kind of get us towards this goal? Well, if what we want to do is we want to pick an input signal that kind of drives at least a piece of the state down to 0, then it seems like maybe a reasonable condition to ask is that our system is stabilizable, right? Because if we have stabilizability, we should at least be able to pick some sort of feedback control law, which will drive our entire state down to the origin. Okay? So a reasonable conjecture is we can get feasibility if we have that A comma B, where A and B are system matrices above, is a stabilizable pair. Okay? So this is our first guess as to what we require for feasibility. All right? Seems like a reasonable condition. So this is maybe what we want in mind for feasibility. Now, what sort of conditions might we need to actually achieve desirable asymptotic behavior? So what do we desire from the solution? Okay, so let's assume for a moment that it is feasible and we are able to solve it. What do we actually want out of our asymptotic behavior of our system? Well, something that's desirable is that our optimal solution, our optimal control law, makes the system origin globally exponentially stable, right? Now, how can we actually achieve global exponential stability from this control law? Well, let's say we get finite cost. Okay? So we'll assume that AB is a stabilizable pair, right? Now, we get some control law as a result that gives us finite cost. Now, what conditions does this enforce on our system? Well, as we said above, right, we have xk transpose q times xk will converge to 0, okay? Now what we have is that if q is positive semi-definite, then there exists a matrix C such that q equals C transpose C, all right? So if we're trying to figure out, if we actually get global exponential stability, maybe we want to kind of examine what's happening to our state vector x in more detail, okay? So by using this decomposition, q equals C transpose C, maybe we can kind of figure out what's happening with x, right? So if I plug this in, then what I get is x transpose times C transpose times C times x will go to 0, all right? Or in other words, the 2 norm of C times xk, 2 norm squared, will converge to 0, okay? So if I want global exponential stability, what do I need? Well, I need that C times xk, 2 norm squared going to 0, implies that my full state vector, xk, goes to 0. Now, see if you could think for a moment about conditions on this matrix C under which this thing actually occurs. Let me draw this as a better K. All right, so I'll assume you've given this some thought. Now, maybe something that you came up with is A, C needs to be a detectable pair. Detectable pair. So you might recall that, we say that AC is a detectable pair if, all of the kind of unstable modes of our system are observable, okay? So in this case, what do we have? Well, if C times xk goes to 0, then, if our system is detectable, then that should imply that the full state vector xk goes to 0 as well. Because basically what we'll have is that the observable part of the state vector needs to go to 0, because we need to be able to reconstruct the full state from our observations, or at least the unstable piece of our state from our observations. And this remaining piece, which we can't detect, is already stable, so that it already goes to 0, okay? So our conjecture is that when AC is a detectable pair, we'll get that C times xk going to 0 is sufficient to get xk going to 0. Right? Because we know that if CXK goes to 0, then our observable piece should go to 0, right? And then our unobservable piece is already going to 0 because we have stability as a result of detectability, okay? So these two basic conditions for getting global exponential stability out of this infinite horizon LQR problem, right, where we assume AB is a stabilizable pair, then we perform this decomposition of this Q matrix and say that AC is a detectable pair. This seems to be a good guess for what we need to get desirable asymptotic behavior out of this infinite horizon LQR problem, okay? So it turns out that this conjecture is exactly true, all right? So before I state a theorem regarding this, I just want to kind of see if we could guess what our actual optimal control law should be for this problem, okay? We've now kind of sketched out some basic conditions under which we think we get a solution. Now, what should the optimal control law be? So a nice strategy for kind of guessing our optimal control law is to examine what happens to the finite horizon solution as n goes to infinity, all right? So this is a nice guess, right? Since if we take n to be really, really large, then it seems like our finite horizon solution should kind of converge to our infinite horizon solution, right? If I take my horizon to be super big. So what do we think will happen to this finite horizon LQR solution that we had up here? Let's take a moment to think about this, right? Now, if I take this terminal condition over here, Pn equals Qf, and I send this off to infinity, what's going to happen as we start to step back? Well, maybe what will happen is if this thing actually converges, right, maybe we'll get that as k is small, right, compared to this huge horizon, these pk's might actually start to converge to something, right? And what they'll converge to is a fixed point of this discrete time Riccati equation, okay? So we take n to be super large, and we kind of step backwards in time to solve for these pk's. These pk's will eventually kind of grow close together, right? They'll grow convergent. And once they do this, right, we should have the same matrix P appearing on both sides, right? PK and PK plus 1 should kind of be the same if we're converging, all right? So what our guess is that the PKs converge to a P such that P is a fixed point of this discrete time Riccati equation, right? So if we plug this in, we'll get that P equals A transpose times P minus PB times B transpose PB plus R, all inverse times B transpose times P times A plus Q, all right? So PK converges backwards in time, right, because our recurrence is going backwards in time to a fixed point of the discrete time Riccati equation. Okay? And our guess was, as we send off n to infinity, then, we keep stepping backwards in this recursion. If this recursion should converge, right, then these PKs should kind of grow close together. And if these PKs grow close together, then we could have the same P and PK plus 1 on either side of the equation, right? So we should get a fixed point of this equation, all right? Now, our second guess is that our optimal control law will then just be an optimal control law with P, right, the solution to this fixed point, plugged in the place of PK, all right? So our solution is U star at K equals minus B transpose P times B plus R inverse times B transpose P times A times X, okay? So this is going to be our standard finite horizon solution just with this fixed point P plugged in instead of our standard PK plus 1. Right? Because the PK plus 1s are going to converge for any finite sort of value of K. All right? So what our guess is we have some sort of matrix P, which comes out of this equation over here, and then based on that equation, our optimal control law will be the static state feedback control law. Okay? Now further, what we say is that all of this should sort of work provided AB is stabilizable and AC is detectable. Okay? So these are kind of some big conjectures that we've made, right? But it turns out all of this is actually exactly true, okay? So I'm going to state this as a theorem. Now, we're not going to have the time to prove this today, but kind of the heuristic idea behind it is all these different elements which we just discussed, okay? So my theorem will be infinite horizon, LQR problem. What are we going to say? So we'll say, consider the discrete time infinite horizon LQR problem. Now what we'll say is, let me actually write this problem out because I'm going to talk about Q versus C in a moment. So I'll say the infimum over U subset Rm, X subset Rn, of our infinite horizon LQR cost, K equals 0 up until infinity of X at time K transpose Q, X at time K, plus U at time K transpose R times U at time K, where here Q will be a symmetric n by n matrix, which is going to be positive semi-definite, okay? And R will be a symmetric m by m matrix, right? Where as standard, R will be strictly positive definite, okay? So let's assume that A comma B, forgot my constraints here, xk plus 1 equals axk plus buk, and then x0 equals some x naught. Okay, so what I'm going to do is I'm going to assume that AB is stabilizable, and that A comma C is detectable, right? Where C is going to be this unique matrix such that C transpose C equals Q, okay? Where then the following two things are going to hold, okay? So first we're going to get a condition on P, right? Which is kind of this conjecture that we just made up here. So it's going to be called the Riccati equation conjecture, or rather, the Riccati equation theorem. So Riccati equation, what we're going to say is for every initial condition, which I'll call P naught in Sn, where P naught is positive semi-definite, the limit as k goes to infinity of the recurrence P times k plus 1 equals A transpose pk minus pkb times B transpose pkb plus r inverse times B transpose pk multiplied by A plus q. This limit exists and is positive semi-definite. Okay? So note that all that I've done here is I've just defined this limit as the standards, as the limit of the standard Riccati equation convergence, or recurrence. My gosh. Where now I've just swapped k and k plus 1 such that instead of the recurrence going backwards in time, it goes forwards in time, right? Because we like taking limits and forwards in time, okay? Now further, what we'll say is the limit p equals the limit as k goes to infinity, pk is the unique positive semi-definite solution of the equation P equals A transpose P minus PB times B transpose PB plus R inverse B transpose P times A plus Q. All right? This equation is called the discrete time algebraic Riccati equation. Okay? Or, as it's sometimes abbreviated, DARE. Okay? Discrete algebraic Riccati equation. Okay, so what we're saying is, under the conditions of stabilizability and detectability, we're going to have that this Riccati recurrence, which we defined earlier, actually converges as k goes to infinity, right? Now its limit is going to be positive semi-definite, and further, its limit is going to be the unique PSD solution of this discrete time algebraic Riccati equation, right? Where now, instead of a recurrence, we just have this fixed point equation, okay? Now, as a quick side note, if we strengthen our conditions to A be controllable and AC observable, then you'll have that P will be strictly positive definite instead of just positive semi-definite. Okay? So that's our first condition. Now, what's our second condition of our theorem? Second, we're going to talk about the optimal control law. Okay? So optimal control law. All right? So the optimal control law for the problem is the static full state feedback control law, which I'll call U star at time k equals minus B transpose PB plus R inverse times B transpose PA times X, right? Where P is the kind of unique solution to this discrete time algebraic Riccati equation up here, okay? So what else do we have? Does this guarantee us stabilization? Yes, okay? So further, the closed loop system is globally exponentially stable when this control law is applied, okay? So what this means is that A plus BK times LQR infinity is a Schur matrix, all right? Where, remember, a Schur matrix is a stable discrete time matrix, okay? All right, So what this tells us is that the solution to our infinite horizon problem is guaranteed to exist under the assumptions of stabilizability and detectability. Now it's going to be written in terms of this P matrix, which is the solution of this algebraic Riccati equation. And further, the optimal control law will actually be a static full state feedback optimal control law. All right? It's actually pretty amazing, right? We haven't said anything about linearity or static state feedback in our optimization problem formulation. This is just something that naturally falls out of this optimization problem. Okay? Now, further, we haven't actually explicitly said anything about stability in our optimization problem. Right? We didn't specify that our control needs to be stabilizing. Right? Turns out stability is kind of something that also falls out of this optimal control problem. Okay? So the proofs of this. The proof of part 1 is a little bit technical. I'll include a proof in the notes, but it effectively follows from this idea that the pKs converge backwards to a fixed point. Okay, so the pKs converge to a fixed point of the Riccati recurrence. And then for part 2, there's a really nice proof of stability that follows from a relationship between the Riccati equation and Lyapunov equation. Okay, so this is one possible proof. You can get another proof just using that the cost is finite and c times xk needs to go to 0. Okay. Otherwise, you could show that when you apply this optimal control law to the system, the Riccati equation really kind of resembles a Lyapunov equation. All right, and using this Lyapunov equation, you can make claims about stability. All right. So again, I'll include a proof in the notes of this, but this one is a little bit more technical than the previous theorem. Okay? All right. So this kind of concludes our discussion of discrete time LQR, right? Where we see that our optimal control law is linear, static, full state feedback. Right? Something that's really kind of impressive, right? Turns out this class of apparently really simple controllers, which we introduced the other day, is actually optimal for this really powerful optimization problem. Okay? So what I want to do just in the last minute is talk super briefly about the continuous time case. All right? So 3, the continuous time LQR problem. And just for the sake of time, I'm just going to give a very high-level overview of the results here. Okay? So it turns out you can derive a solution to the continuous time LQR using the Hamilton-Jacobi-Bellman equation, right, which we discussed very briefly towards the end of last time. Right? This is this continuous time analog of dynamic programming. Now, it turns out this solution is much, much easier than the discrete time case. Okay? So the algebra works out a lot nicer, and you really get some pretty nice clean solutions. Okay? So what you'll find is that the optimal solution, so the optimal control law, solving your your continuous time problem, right, which is inf over u and x of t transpose qf, x of t plus the integral growing from 0 until time t of x of tau transpose q, x of tau, plus u of tau transpose r, u of tau d tau, subject to x dot of t equals ax of t plus bu of t. There should be an x of 0 equals x naught. So the optimal control law solving this problem is going to be given by u star at time t equals this minus r inverse times b transpose p of t times x, where p of t is now the solution to a continuous time version of the Riccati equation. This is now going to be a differential equation. Okay, so just like how in discrete time we had a recurrence which generated this p matrix, in continuous time we have a differential equation. It's going to be minus p of t times a plus a transpose times p of t plus p of t times b r inverse times b transpose p of t minus q. Okay, so this is called the continuous time Riccati equation. Okay? So once again, your optimal control law in this continuous time case for the LQR problem will be a linear time varying state feedback control law. Okay? Now your infinite horizon case, solutions will exist under same conditions as your discrete time. Okay? Now what you're going to get is you're going to get that U star of t equals minus R inverse B transpose P times X, where now, again, we have a stationary solution, right? Oh, I forgot my final condition over here. P at time t equals QF, right? Same sort of boundary condition as before. What we're going to find over here is that here we'll have the P matrix will be the solution of 0 equals, that shouldn't be a minus there. It should be PA plus A transpose P plus PBR inverse B transpose P minus Q, okay? So it turns out in this case, we can really similarly kind of get solutions to our optimal control problem using another sort of Riccati equation. So I've just realized that I've actually made a couple of typos over here. This was meant to be a minus plus, it should be a minus P dot. Okay, there we go. That's better. And then if we go ahead and we flip all the signs down there, that should be a plus Q. Okay, and then we swap this to a minus. All right, that's looking better. Whoops. Okay, there we go. My goodness. All right, so our general takeaways for this continuous time case are that our solutions really pretty closely mirror this discrete time case, right? Only now we're going to have this continuous time analog of the Riccati equation, which is a differential equation. But other than this, our solution still takes on a fairly similar form, right? We have in the finite horizon case, we have this time-varying linear state feedback control law. And in the infinite horizon case, we again end up with a static state feedback control law as being optimal. Okay? All right. Thanks for watching.